Hello everyone, my name is Alex Cheng and I'm a junior at Hillcrest High School in Midvale, Utah. And my project this year is looking at this type of blood vessel growth in the eye known as intravitreal neovascularization. And so before I begin, I'd like to define a few terms. And so here you can see this is an image of the eye, and if you have this eye in your body, the light would come here. And so the retina is along the backside of this eye and it receives all the light. And so there's this disease known as a retinopathy of prematurity, or I'll refer to this as ROP. And this is the leading cause of childhood blindness in the world. And so with retinopathy of prematurity, this can cause this type of blood vessel growth known as intravitreal neovascularization, or IVNV. And what this is when the blood vessels grow from the retina upwards into the vitreous of the eye. And so vessel growth in the eye is very important because if you have abnormal blood vessel growth, you're going to have visual impairment or blindness. And so since ROP has been linked to IVNV, it suggests that IVNV can be a reliable indicator of ROP. And so, however, the methods of detecting IVNV are extremely slow and manual, and so I wanted to create a faster and automated way of detecting IVNV, and so then we could detect ROP faster. And so here you can see two images. These are the images that I was analyzing, and they're called retinal flat mounts. So retinal flat mounts are these retinas cut open and laid on a flat surface. And so here you can see this is IVNV growth, because you can see how these blood vessels seem to be growing upward, and they're very abnormal. While in a normal retina, you have this uniform growth. So I wanted to see if I could detect this IVNV growth. And so my goals for this project were to create an automatic way to detect IVNV, and also to have a minimum accuracy of 95%, so it could be used in the clinic. And so to do this, I was able to obtain 14 images from the Moore Eye Center at the University of Utah from my mentor at the HeartNet lab. And so these images were manually marked, and so all of the IVNV had a reader go into them and manually mark out each IVNV individually. And so these images were also very, very large. They were over 10,000 pixels by over 10,000 pixels. And so since they were so large, when I first began running it on my own computer at home, I ran it and I checked on it every day for 2 weeks, and at the end of 2 weeks, it still wasn't finished. So I had to use something much more powerful, and so I went to the University of Utah and I used their supercomputer, the Kepler cluster. And the reason I could use this and process these images much faster is because it has GPUs, graphical processing units, and that can process images much faster. And so initially when I began this project, I started using Caffe, an artificial intelligence framework. However, I quickly switched to TensorFlow because I realized that was much more compatible, and I'll explain that later on. And so I also used the imaging software Fiji and ImageJ because that's the software they were using at the HeartNet lab where I got my images. So I had to use that. And then I wrote my code in Python. And so when I first received these images, I looked at them and I realized that they were all different variations in brightness and shade. And so to fix this, I wanted them to all have the same brightness because you don't want a ton of variation across your images. So to do this, I used histogram normalization. And what that is it takes the lowest pixel value of the image and sets that to 0, and then the highest pixel value of the image and sets that to the maximum pixel value it can be. And in this case, since these were all 16-bit images, that would be 65,535. And so you can see here the histogram. In this not normalized image, you have all these pixel values closer to 0, whereas when you normalize it, you bring this range out and it expands. And what this ends up doing is it makes all the images the same range, so you can analyze them equally. And it also increases the contrast in the image, so you can identify IVNV easier. So after doing this, I was able to create masks. And what those are a way for my method to learn what is IVNV and what is not IVNV in these images. And so in these masks, you have white and black pixels. And so this white pixels would represent the IVNV, and these black pixels would be non-IVNV. And so these masks were created from the manual markings that you can see here of the HeartNet lab. And so from these images, my method would be able to learn what is IVNV and use that information to predict future images for what is IVNV in those images. So after doing this, since these images were so large, I had to split them up so that it wouldn't run out of memory when analyzing one image. So I split this up into a grid, and a 7x7 grid, so vertically and then horizontally. And instead of analyzing the whole image, I would analyze each 7x7 image and so that it wouldn't run out of memory. And the The reason I split it into 7 by 7 was because by splitting it up into 7 by 7, I could also remove some of the background, and that would reduce processing time as well. And so my method was based on convolutional neural nets, which have been proven in the past to be a very effective form of deep learning that can classify images. So for example, if you have an image of a car, it's able to tell you there's a car in this image. And if you have an image of a plane, it's able to tell you there's a plane in this image. And so the three main layers in a convolutional neural network are convolution, ReLU, and pooling. And I won't go into too much detail due to time restraints, but basically how these work is that they're repeated over and over. And so you have this original image, and it reduces it into a smaller feature map that represents that image, and it uses that smaller feature map to say what class that image is in. However, I didn't want to just do classification. I didn't want to just say if this image has IVNV in it or not. I wanted to be able to tell where in the image the IVNV was. And so this process is known as segmentation, not just classification. And so to do this, I implemented a fully convolutional neural network. And what that does is it takes that convolutional neural network and has that feature map at the end, except it takes that small feature map and upsamples it back into its original size to produce a predicted image for the segmentation. So you can see here that it will produce this very small feature map and change it back into its original size, and then produce this predicted map for where in the image the IVNV will be. And so, like I said, I tried to initially implement this with Caffe, and I switched to TensorFlow. And the reason for this is because TensorFlow has much more user documentation. It was open sourced in 2015, whereas Caffe has a little less documentation. And so since TensorFlow is more compatible with fully convolutional neural networks, I switched to that. And so while designing this fully convolutional neural network, I had to select a few parameters. Most notably, I have 3 parameters here that I'll talk about. So the number of classes, which was IVNV and non-IVNV, and then the batch size and epoch size. And so the batch size is the number of images that it takes in every time it reads and trains on it. And so, so it would take 2 images in and learn from them, and then iterate through another 2 images, and then iterate through another 2 images. And so then the epoch size is the total number of times it goes through the data. So the epoch size, so since it was iterate through all the images, it would do that once, and then it would do that again, and 20 times over. So that's the epoch size. And the reason I chose these parameters is because you don't want the convolutional neural network, the fully convolutional neural network, to go through the data too many times, or else this causes the method to overfit on that one set of data. Because if you're only able to predict that one set of data, when you have a future image, you're not able to predict IVNV in that image. So by doing this, I could predict IVNV in future images as well. And so now that I was able to design my fully convolutional neural network, it would produce an image like this, where it would predict out the IVNV and the non-IVNV areas. And so to compare that to the ground truth, I would use pixel accuracy. And what that is it takes the total number of correctly identified pixels, so both IVNV and non-IVNV pixels that were correctly identified, and divide that by the total number of pixels in the image. And the reason I did it this way is because it can determine what locations the pixels are into. If I had just compared area, then it wouldn't be able to compare where the locations are. But by doing it this way, I was able to compare where the location of the predicted IVNV was. And so you can see my results here. I used a 3-fold cross-validation. And so what that means is I would split my data set up into 3 parts, and the first 2 parts would be used as a training group, and then the third part would be used as a testing group. And so then it would switch over and use different 2 training group sets, and then use the second for a test group. And so for my first validation, you have an 88.8% accuracy, and 78.9 and 92.6. This is an average accuracy of 86.8%. And the reason I use cross-validation is, again, to prevent overfitting. Because if you train on all 3 of your subsamples, then it will only be able to predict on those subsamples. And so based on these results, this is seen as a promising tool to predict IVNV in the future. Most notably, it is much faster than the current methods of detecting IVNV, because what they have to do is they have to go in and manually mark out each of these. And they're very small, and so it takes a lot of time. That takes a long amount of time, whereas my method, it takes less than 1 second to predict one of those 7 by 7 images. And although this did not achieve a 95% accuracy, it shows a lot of promise, and it shows that there's a much better way to identify IVNV and thus help progress the treatment of ROP in the future. And this project was also hindered by a lack of images. And so because of my 86.8% accuracy rate with only 14 images, convolutional neural networks usually have around 1,000 images. And so if I had more images, it could potentially raise my accuracy as well. However, that's not the only error that I noticed in my images. And so, for example, you have debris in these images. And what these are these bright white spots in these images that appear very similar to IVNV. And so you can see how the IVNV is bright and white, whereas this debris is also bright and white. And so what that would cause the fully convolutional neural network to do is to overpredict the amount of IVNV in the image. However, this isn't as harmful as underpredicting the amount of IVNV, because if you underpredict the amount of IVNV, that's signifying that the patient may not have ROP, right? But if you overpredict it, that's just saying that this ROP is more severe. And so having it overpredict was not as harmful. And also the parameters I chose for my fully convolutional neural network could also have led to some error. And so to fix these, I'd like to, in the future, possibly ignore the debris. And how I would do this was that I noticed that the IVNV growth usually happens on the perimeter of the retina, whereas this debris can occur in the center as well. So if I was able to ignore the center of the retina, then that would reduce my error as well. And so regarding the parameters, I could go into unsupervised deep learning, which is where where it's able to learn by itself, and I wouldn't have any manual input. So I wouldn't have to tell what's IVNV and what's not IVNV. And also, I would like to explore different fully convolutional neural networks in the future. And so here are my works cited. And I'd like to thank my mentor, Dr. Tolga Tazison at the Scientific Computing Institute and Imaging Institute at the University of Utah, as well as the HeartNet Lab, and my mentor there, Dr. Mary Elizabeth Hartnett. Thank you so much.